Okay, today we're going to be continuing an education video series, and we're going to be talking about a common mistake in analysis in schools. Especially when a school is just trying to do some scrappy data analysis, and it has to do with doing math with percentiles. It's not allowed, and it turns out that it leads to wrong conclusions when you try to do subtraction or averaging with percentiles. There's an easy fix called the normal curve equivalent. We're going to try to cover this quickly, but make sure that you actually understand the theory as well. So, I want you to imagine that you are a math teacher and the district math coach comes into your department meeting and they say, "We've got a strategy, but first we're going to show you a table of data and you're going to help us think through what to do with this." All right, so we've got teacher A, teacher B, and teacher C, and they have the prior year percentile rank of the students, the average of those students. So what that means is they took all the students taught by teacher A and they looked at their prior end of year test and what their percentile was. Then they averaged all those percentiles. Now, at the end of the current year that's just finishing right now, we've got the current year end of year average percentile for those students of teacher A, teacher B, and teacher C. Now, you can quickly see that teachers A and B had students coming in at a higher incoming ability, and teacher C has students coming in at a lower incoming ability. But you might think, let's talk growth. Subtract these. So, this teacher A grew their students by 8 percentile points, teacher B grew their students by 10 percentile points, teacher C only 5. And what's going on here, the district math coach says we've got a strategy, and that is we've looked at your growth, and while all of you are doing great and growing students a little bit faster than typical growth norms, because remember, typical growth norm would be you get a bunch of students at the 5th percentile, you grow them at about the typical growth for typical 5th percentile student, and they end the year at the 5th percentile. So all these teachers are growing their students faster than typical, but the district math coach says, we've seen that teacher B is probably the most effective of these three. And teacher C might be the least effective. So, next year, hey, teacher C, why don't you get some mentoring from teacher B, see if you can improve the growth, and you could grow your students by 10 percentile points too. Makes sense because, the students that are furthest behind, we really want them growing as the most. So, and by the way, there's a bonus for any teacher that grows their students by 10 percentile points. Teacher B, you're getting the bonus. Congratulations. Okay. Here's another sort of a thing that you might see in a school setting. Okay, we've got students A, B, C, D, E, F, and G. We've got their beginning of year percentile rank and their end of year percentile rank, and we're trying to figure out, okay, let's see, maybe we should pick the student that's most improved and give them an award. Well, you can quickly scan down this list and see that we should give the student as the most improved to student A. They grew by 11 percentile points. What I'm going to tell you before we get any further is both of these conclusions are very wrong. And it's because somebody didn't know that doing math with percentiles is illegal. So here, the math that they were trying to do with percentiles led to the wrong conclusion. You're going to see why in just a second. Here, same thing. It turns out that student A is not the most improved. And you're going to understand why in just a second. But what I need you to understand right now is never subtract and never try to take averages of percentile ranks. Use another tool instead. Before we get there, what does a percentile rank even mean? If you look at this diagram right here, okay, you can see all these smiley faces, and I've actually drawn 100 smiley faces as if they were 100 students under this bell curve. And in life, things tend to come in bell curves, whether it's how fast you can run or your score on a standardized test, okay, or the number of points that you earned on that standardized test. And a percentile rank is just how many students out of 100 typical students, how many of those students would be scoring lower or running slower than you. It's basically like, look at this bell curve of students, and if I'm this student, I'm at, let's just say, the 80th percentile rank, because if I count up all the smiley faces to the left of that smiley face, there's 80 of them. And so if you look here, here's the first percentile rank, second percentile rank, third, fourth, and fifth. And out here is the 99th percentile rank. Now you know what percentile rank is. And just to remind you that bell curves are everywhere, here's another bell curve. It's like a classic stats professor thing. They have everyone write down their height, and then they bring them to the auditorium and they say, all right, everybody line up in behind the person that's holding a sign for your height. And you can see at least the median and the mode of this class look like about 5'6", 5'7" for the average, median, and mode of the class. And the highest is 6'1", and the lowest is 5'0". And it's a bell curve. There's more in the middle, just like I just showed you here. And that's going to be true with percentiles as well. Now it comes to a thinking question. Which is harder? And this, if you can think this through, you're going to understand everything so much clearer. Which is harder? I'm in a race with 100 people. Which is harder, moving up from the 50th place to the 49th place, moving from the 100th place or last place in this race with 100 participants, and moving up from the 100th place to the 99th place, or moving from second place to first place? Think about it for just a second. Okay. Well, it turns out that these are not all the same difficulty in terms of how much you'd have to improve in your running ability to make this change. If you go to a cross-country race, you're going to see at first there's just one person crossing the line, okay? It's a little bit like this bell curve. The person in the front of the pack is going to come, and then it might be 40 seconds until second place comes across the line. And then it might be another 10 seconds until the third place runner. And then all of a sudden, we get more and more towards the pack or the middle of the running group. And now you've got somebody crossing the line every second, or maybe 2 or 3 people all crossing in the same second. And so here's the answer to your question. Moving from 50th place to 49th place is very easy. You might just have to put on a final burst of energy and get a half second shaved off your time, and you went from 50th place to 49th. However, moving from last place to the second to last place might take you cutting 30 seconds off your time. Similarly, moving from second place to first place might take you really cutting your time, because remember, in a bell curve, the fastest person in the group is actually probably a fair bit faster than the second place, okay? You might really have to improve to pass one person when you're already at the tails of the bell curve, okay? And so, bringing this back to a school setting, I showed you that at the beginning, a list of students and how much they improved. One of them went from the second percentile, that's this little smiley face, to the 11th percentile rank. And we might say they moved 9 percentile ranks. Let's look at another student that moved from the middle of the pack, 50th percentile rank, to the 61st, or percentile rank of 61. And we might say, oh, they moved by 11 percentile ranks. But here's the thing. It turns out that the length of this arrow and the length of this arrow represent the amount of learning that they would have had to grow past average growth in order to pass others in the test. And so actually the person moving from the second to the 11th percentile rank grew a lot more. Let's just say they grew 3 weeks extra this year compared to typical growth, where this person only grew 1 week extra this year compared to typical growth. So who's the most improved student? Well, it certainly actually is this person who grew 9 percentiles, not this person who grew 11 percentiles. Your big takeaway here is that adding, subtracting, multiplying, dividing, all mathematical operations on percentiles or percentile ranks, they're illegal. And the reason for this is that percentile ranks are not an equal interval. Equal interval just means that the difference between two numbers that are right next to each other on the number line is logically the same everywhere on that number line. Equal interval could mean that the difference between 31 degrees Fahrenheit and 32 Fahrenheit is the same as 70 to 71 degrees Fahrenheit. But with percentiles, it's not that. Percentiles are not equal interval, and we need a replacement that would be equal interval. So we got 3 good solutions. One is you could use raw scores. Instead of using the percentiles, just use the raw score on the test. Or if you have a scale score, that'll probably also work pretty well. And scale scores would apply more to standardized tests or something that's statewide. Using z-scores is another option. For those of you who have some sort of statistical training, you know what a z-score is. And I'm not going to go into depth besides to say that an NCE, or a normal curve equivalent, is a little bit like a z-score, except it's rescaled to go from 1 to 100, kind of like educators are used to working with numbers in that 1 to 100 range. So let's look a little bit about NCEs and percentiles, and we're going to discover that NCEs are a quick swap in for percentiles that let you do math. So that where averaging and subtracting percentiles was illegal, but not with NCEs. Let's look at the conversion between percentiles and NCEs. First off, these two scales are anchored in 3 places that are always going to be the same. The first percentile is the same as the first NCE, 50th and 99th. They're the same, okay? And so you can kind of interpret an NCE a little bit like a percentile. Whenever you see NCE of 1, that means pretty far towards the bottom of the distribution of scores. NCE of 99 is just the same thing as the 99th percentile. Here's where they start to be different. Where the 25th percentile is right here, so follow this green 25 up, and if you counted, you'd find 25 smiley faces to the left of that. That's because it's the 25th percentile. 25 out of 100 typical students are scoring lower than you. And 75 is here. The problem is that with percentiles, the distance from 1 to 25 is not the same as the distance from 25 to 50, 50 to 75. And NCEs solve that by just saying, you know what? We're going to anchor it at 150 and 99, and then 25 is just going to be halfway in between 0 and 50, or halfway in between 1 and 50. 75 is going to be halfway between 50 and 99. And so NCEs are anchored at 3 places, but rescaled so that they are equal interval, meaning 10 NCEs of growth at any point in the scale is equally to be celebrated, okay? Or similarly, 1%, 1 NCE of decline in your score is a similar amount of regression relative to typical growth. And what you'll see here is that 25th NCE is actually the same as the 12th percentile rank. And so we need some sort of a formula that'll take us from 12. Whenever you see a percentile, you could turn it into that 25, and now you'd be able to do math with it. And I'm going to give you that formula in just a second, but your takeaway is that NCEs are equal interval, and you can do math with them. And they're also useful because educators like that 1 to 99 or 0 to 100 sort of a scale, because that's what test scores are reported in, percentiles. People are used to interpreting them. So let's take the group of students that I showed you at the beginning of the talk, and we're going to take their percentile ranks, and instead of doing this illegal thing, which is subtracting their end of year and their beginning of year percentile rank, we're going to convert it to NCEs before we do math. And the way for you to do that is real simple. Just Google normal curve equivalent, or NCE, on Wikipedia. You're going to find a very simple Excel formula. And I use that Excel formula to take my first column of beginning of year percentile ranks and turn it into my third column of beginning of year NCEs. Same thing with the second column and the fourth column. Now I've got all of my percentile ranks transformed into NCEs, and now it's legal, statistically legal, for you to do math. Let's subtract. 56th percentile at the end of the year, 50th at the beginning of the year, subtract them, and student A grew 6 NCEs faster than typical growth over that time. Cool. All right. Now student B fell backwards a little bit, so that happens. Student C grew. Student D grew by 17 NCEs. Remember, this is the student that in our initial analysis grew only 9 NCEs, and we thought, well, a lot of students grew more than them, but it turns out because they were starting so far behind, they grew 9 percentile ranks, and it felt like a lot of other students grew more than them, but in terms of true growth, a true measure of growth units, that 17 actually makes them stand out as the most improved. So it really should be student D getting the most improved reward this year. And going back to the beginning, where we were asking which teacher is possibly helping students grow most effectively, we were asking the wrong question at the beginning of the time when we were looking at which of these three teachers grew their students the most. And that's because we were using the word average percentile. For the rest of your ed data career, I want you to never, ever use the words average percentile because it's illegal. And NCEs is a quick replacement that lets you make valid conclusions. So we're going to scratch through every average percentile and we're going to say, convert them to NCEs, find out what the NCE growth was. And now we can compare two teachers and compare the growth of their students. Two caveats. It's still better for you to use scale score data if you have it, or raw score data if you have it. And so it's not necessary for you to fall back on percentile ranks converted into NCEs if you actually have, like, say, a RIT score on the map or something else that we believe to be sort of equal interval. My second caveat for you before you start using NCEs on everything is that you need to make sure that you believe the underlying data is normally distributed, and you can check this assumption just by looking at it. If the national scores on a test or the norming scores on that test have a lot of students sort of maxing out, getting the max points on it, well, then we don't think that this is normally distributed in the national population. It's almost like giving a second grade test to a bunch of fourth graders. Most of them will test out of it. And now percentiles don't really mean anything when we've got a test that a lot of people are testing out of. Similarly, if a lot of people in my norming population or like the national population were scoring off the bottom of the score range, you really can't use percentiles and you can't use NCEs. I'm going to tell you one more really useful thing about NCEs and then we're more or less done. I don't know if you've noticed, but standards change, and so do testing vendors. And they change a lot in America because we don't have a national test, and we don't have a national test creator, and we don't have a national test vendor. Each state gets to pick their standards. They might collaborate, say like they did on Common Core, but then states might say, no, we don't want to be part of Common Core, and we're going to do something different. And states might pick every few years, we want a new test vendor. Well, different test vendors and different standards lead to different scale scores. And so if the average scale score in 2023 is a 55, and then let's say the test vendor changed, and now the average in 2024 is a 720, how do you compare 55 and 720? They're clearly on different scales. So in a case where you have scale scores and you have raw scores, but it's clear to you that they're not comparable, fall back on NCEs. Almost certainly the old test vendor is going to give you percentile ranks and the new test vendor is going to give you percentile ranks. And you can kind of assume that, they're both measuring fourth grade reading. They're both measuring the same sort of thing. Let's just go ahead and say that the percentile ranks are probably pretty comparable between the two scores. And then we can compare students and see which students grew and which students fell back by first taking percentile ranks, turning them into NCEs, and now we can do some math on it, okay? So glad you took time to listen to this. At United Infolytics, one of our things is we really love empowering educators, schools, to use data to make valid conclusions, to really understand their data. And part of that's with helping you do the one-off analysis and doing it the right way. But the other thing that we'd love to do for you is help you think about dashboards or other tools that your school needs to run efficiently and have data at its fingertips. So if you want to talk more, Nate and I would be happy to talk to you about the things we can do for your school. Otherwise, just keep on watching these videos, pass them on to your ed data person, keep getting smarter at doing the right analysis that leads to the right conclusions, because education is important business, and making the right conclusions leads to the right policy, and the right policy is good for students. So thanks for listening. I hope you find this useful. If you do, let us know. Thanks so much.